Hello everyone, and thank you very much for giving me the chance to speak today. I look forward to it. So my role is I'm a manager of two laboratories at Stellenbosch University in South Africa. We're just outside Cape Town, and we basically have two facilities for neuromechanics research. And my role is to oversee the delivery of analytical services to researchers who are wanting to use equipment for their studies. And we do everything from maintaining the equipment to coding different analytical solutions. So we do a lot of programming work, we do consultation on the experiments that people are doing, and so on. And my background is in engineering. I did my postgraduate studies in biomedical engineering, also at Stellenbosch University. And yeah, one of the things we do at our unit besides research is consultancy to companies and to individuals doing research and development or validations of their tools and so forth. So that's sort of my background in brief.
Today we're going to talk specifically about IMUs. Can you give us a little bit of your history in working with IMUs?
Sure. So I actually did my master's and PhD studies using IMU technology. We bought one of the early systems that came out in the early 2000s, and my study was to use the system to analyze cycling biomechanics, and we actually did some really exciting stuff at the time. We followed people on their bikes out on the road, and they were wearing these sort of wetsuits with the sensors in, and we were able to collect information about how they were cycling in 3 dimensions on the bike. And yeah, so I've been doing that kind of thing since then. We've been doing so many different kinds of studies now. We have healthcare projects, so people doing things with rehab. We're using it in the sports kind of space. And so IMUs have become a very important part of what we do at our lab, amongst other things. And I've been able to, had the privilege to join in a lot of these different types of studies. So kind of been in it for just over 10 years now.
And I think you've worked a little bit with the Neuraxon IMUs. Can you also share a little bit of your interaction with Neuraxon and maybe when you got started with any of our equipment?
Yes, so about 3 years ago, we were looking to expand our mobile platform to try and do more research outdoors. We had a lot of people trying to collect data in rural areas. Here we have a lot of communities and populations groups that we couldn't really bring to the lab, so we were looking for ways to measure or at least analyze these types of people in their own environment. And so we looked for something that could measure all the things that we were trying to measure in the lab outdoors. And yeah, it was really just a matter of looking at what there was in the market, and we started working with Neuraxon because we felt that they enabled us to kind of connect all of our devices and look at everything in one space on the software side. So yeah, it's been about 3 years, and we started asking a lot of questions to the Neuraxon guys, and I think from there we formed a partnership. It's been really a great ride, just learning about this field and working together with them, partnering with them, you guys. So yeah, I think it's been a real nice thing to see the development of this field and the mobile sensing. So yeah, it's been a positive experience.
That's awesome. So with that, I think I'm going to let you get going on what you wanted to talk through today.
Sure, okay. Right, thanks, Erin. So just going to start with a quick background. As most of you know, we're living in an age now of increasingly personalized data and services all around in different industries. And I mean, in our field, I mean, movement analysis, sensor technology is developing and becoming more readily available. And so we're able to measure more things. We're gaining access to more and more information, neuromechanical information about the individual. And these technologies are also becoming more integrated, which is an important advancement because we also want to see all of these things happening at the same time. So technology is improving what we can measure, and it's improving when we can measure it. But a third key driver of personalization I mean, our field is where we can measure it. So here's just a picture of one of the studies that we were doing outdoors. So to measure the natural behavior, we really need to get out of the lab. And this is a setup for one of our sports projects using an optical motion capture system. And following this kind of trend of portability, the optical motion capture systems have developed to the point now where we can collect data outdoors, which is quite a fantastic technological achievement. And this has worked quite well for us in some of our projects, but we've also faced challenges with this kind of setup. So for example, setting up and breaking down the system, it takes about 2 hours to do the whole setup before you start measuring, and it can take about 2 hours to break it all down again. And so when you're working in a busy environment, that's kind of tricky. And also sometimes in some of our projects we have space constraints. So often we're working in tiny, cluttered environments that just aren't suitable for a kind of optical system where we need a really controlled environment. And of course, transporting this kind of technology around for this kind of setup is not really convenient. It takes a lot of space and it's quite heavy equipment and so on. So the deployment really also needs a full desktop PC. So this is really where wearable technologies such as IMUs are coming in and can play a strong role in supporting what we're doing in the research side. And yeah, so I mean, wearable technologies aren't going to replace laboratories, but they do often allow us to escape them. And the thing is, they're very mobile. So we've got these tiny sensors now. They're becoming so compact. They're wireless, they have onboard computing and data storage. So they're really non-invasive and they cost less. And they're often much easier to use without specialized expertise. The big question, though, of course, is do they work well? And this is what we're talking about today. So we're talking about IMUs and how we can get the most out of them. And I want to share some ideas just about how I think about IMU quality, how we can try and quantify that quality, and how we can try to optimize it. So, and then at the end, I just want to touch on an exciting new tool that we've developed for taking your IMU data really, I believe, to the next level. So usually when people think of wearables, they think of sort of low fidelity monitoring devices, you know, the wristwatch accelerometers or the phone-based apps. But what we're talking about here in this webinar is really IMUs that can get us as close as possible to the type of data we're used to getting from our normal lab camera system. And so that's why we're talking not about individual sensors, but multi-sensor systems that can be used in a sort of body network to get things like joint angles and other skeletal data. So many researchers are using these systems and performing validation studies with them. But if you have a look at the literature, you'll see there's quite a lot of variability in what they're finding in terms of the quality of the data. And there's a whole range of things that can affect IMU data quality, from the hardware, the firmware, right through to software features and the biomechanical modeling. So we're going to touch a little bit on each one of those today. I think the best starting point, though, is just to take a wide-angle view of what is going on when you use this technology. So the fundamental goal when we're using a motion capture system is to try and measure where the bones are. So we're talking about their orientation in space as well as their linear position or their translation through space. And because motion capture systems describe movement in 3 dimensions, they use coordinate systems. So it's important for us to be comfortable with this kind of thing. So very basically, when we're looking at a bone tracking using motion capture, we're essentially talking about, first of all, a coordinate system that's attached to the body segment or the bone segment. We could call that the technical frame because it's arbitrary, and we assume that it's rigidly connected to the segment. And then we have a second reference frame or coordinate system, the global frame, and that's attached to the external environment. We usually assume that that's not moving, at least for what we're looking at. Of course, when you have this information, you still actually don't know where the bones are in terms of their morphology. And so to estimate segment morphology, we need a third frame. We call this the anatomical frame. And this is calculated from the technical frame using a calibration. And once we have that, we know where the bones are. So we would have then an anatomical frame for each one of the bones in our skeleton. And so when you look at it like that, it really narrows down the kinds of things that could be affecting your data. Because when you're looking at something in your data, you really need to be asking, is this a problem that I'm noticing that's coming from the technical frame or from the estimation of the anatomical frame, or is it simply the way mathematics is being done in the model to calculate the different things? So really this is how I think about where problems can come from. And so when we calculate something like a knee angle, we're using 2 anatomical frames and some mathematics to get the data out. One of the most underestimated factors that affects the quality of motion capture data captured with any technology, cameras included, is soft tissue artifact. And this is just the error that happens when the technical frame is actually not rigidly connected to the bone or the anatomical frame. And this is something we automatically assume in most motion capture situations. So you can have it where it wobbles like this. You can have sliding of the frame, and you can have twisting of the frame. And all of this results in uncertainties about where the bones are. And so this is one of those problems just important to be aware of, because it affects any motion capture data you'll be working with, including IMUs. So the starting point for looking at your IMU data quality, though, is the motion tracking. So how well are we able to track that technical frame that's attached to our IMU? And I think I just want to cover here a few of the basic ways in which we can think about how this IMU is tracking its own movement. So an IMU uses a range of sensors to feel aspects of its own motion, and these are fused together in a mathematical way, in an algorithm, in an optimal way to estimate the technical frame position. It's much in the same way that your brain senses the movement of your head using pieces of information from your visual and vestibular systems. So an IMU, the heart of an IMU is really the gyroscope, and how it's able to track. It uses the gyroscope data to track its changes in position. It's measuring the speed, and then by mathematical integration we're able to track the fast motions of the IMU. The gyroscope has small little errors in its measurements that tend to add up with time, and many people will know this as drift. This is a typical problem we have with IMUs, is that they have drift errors in the gyroscope data. Also, the gyroscope can't really measure exactly the exact position of where you are, it just knows how far you're moving in different directions. So really, when we think of the global frame for an IMU that's attached to the external environment, really we're talking about a coordinate system. You can just see there the green. This is now, I don't want to over-explain it, but essentially we use a north-east up kind of world frame for IMUs, and the accelerometer in the IMUs, the accelerometers are picking up the up-down direction or the inclination, and this is where we get our pitch and roll angles from, and the magnetometer inside the IMUs is tracking the north direction, and that's giving us our heading or our course angles. And so essentially when you think about this type of tracking, it's important to know the different types of sensors and what they're adding. So it's also important, though, to understand that you need to understand the quality of your sensors that are inside your IMUs that you're using in your practice or in your research lab. And this is a whole field in its own, but it's at least important to know that there is a range of quality available at a range of prices. So cheaper gyroscopes and accelerometers and magnetometers are more noisy, and they work in some ranges of motion and dynamics less well than more expensive sensors. So don't assume that all sensors and all IMUs are the same hardware-wise. Also, more expensive IMUs tend to undergo more extensive testing and factory calibrations and so on to make sure that all the data is being measured well. So let's talk a little bit about how we can determine whether our sensors are tracking their own position very well or not. I just want to start with the most basic test, and that's just to see whether your IMU actually registers that it's not moving. And what I mean by that is if you leave your sensor lying on a desk, not moving, and you measure its position that it's measuring, it should measure a stable position and not drift off or change too much over time. So that's the most basic test. You can just check that your sensor's not broken or anything. And then, of course, you can test it again at maybe a 90-degree tilt. Also turn the sensor onto its side and see that it registers the right amount of rotation when it's stationary again. So you can start off just with static tests, although that's not the whole story. Of course, static tests are not enough. Another important way you can do a simple regular check on your IMUs is simply to see if you stick all your IMUs to a rigid object and you calibrate them to the same starting position, do they actually track relatively the same movement? Because they should if they're rigidly connected. And so I just think of this as a comparison between several IMUs for repeatability between them. So it's an inter-IMU sort of reliability test that you can do with just a simple piece of wood or the charging block that you use. We use our charging block. One of the important things is not to put the sensors too close to each other. They can start to affect each other if they're in very close proximity. But generally, if you space them out and they're working well, they should track the same motion. So we typically would swing the thing around a little bit and see that we're getting the same sort of results. Of course, if you want to go and validate your hardware or your IMU system, then it becomes, you need to have obviously gold standard reference equipment. One of the most kind of quality ways you can check your IMUs, which is not really practical for most people, is to use a sort of rate table. There's specialized equipment that some institutions or companies might have to be able to tightly control how you move the sensor around, and then you can use this to measure whether your sensor measured correctly. But most labs, if they're going to do something like this, are going to use stereophotogrammetry or optical motion capture. This is something that we did, it does take some expertise to do a proper validation of your IMU's motion tracking using a camera system. That's just because they have different global frames, so you need to align those. They have different technical frames because the sensor and the markers that you put on them are not perfectly aligned. And you need to understand various technical things to do with how you process your data on the two different systems. For example, filling gaps in your trajectories for your optical system, smoothing them and so on. That can affect obviously and inflate in some cases the errors that you would see in your IMU system. So you need to be careful that you're getting all of these things right so that you're able to compare apples with apples. A small little note also, the distance between markers when you're using camera systems to validate is very important. If the markers are too close together or too collinear, they tend to give a poor kind of tracking of the cluster that you're using as reference. So there's a lot of little things there. If you're going to do something like this, I would really suggest that you become familiar with all the details. So here's just some basic results we got from our test. So we did a static test and a dynamic test. Our static test, we left the sensors just stationary for a whole hour, which is, I think, I suppose, quite excessive. And we basically just checked that the camera system and the IMUs were registering the same static position, and that was very satisfactory for us, under 1 degree of error in inclination and in heading. And this is just the RMS difference between the two. And then for our dynamic test, we swung them around quite a lot on the wooden beam for 5 minutes, and we still were able to get very decent results. Typically, though, you'll see that the inclination tracking in IMUs is more accurate than heading and also more reliable. That's just because of some of the noise in the magnetometers is just higher. The accuracy and precision of the magnetometers is not as high as the accelerometers, and magnetic fields do tend to be slightly non-homogeneous even in a seemingly clean space. But if we want to start thinking about how can we improve the tracking on our IMUs, I think the most important thing, which is typically the Achilles heel of most IMU systems, is the tracking of north, or the heading or course angle. So magnetic interference tends to create havoc in many IMU systems. Some suppliers have got solutions for this and are providing software solutions to the errors that you see in magnetically dirty spaces. I think the most important thing is just to be aware of the fact that when you're in a building, typically there is ferrous metal in the floors and in the walls. There are magnetic fields around the computer and other IT equipment, around cell phones and so on. So it's very important that when you're managing magnetic interference, when you're doing experiments, it's important to understand the space that you're working in. And typically it's crucial to find a space within your test area where you can calibrate your biomechanical model without there being disturbances. And most motion capture systems, the good ones at least, will have warning systems in place to tell you when your space that you're calibrating in is dirty. We also tend to use a sort of either plastic or wooden step if the floor is just magnetically disturbed. In the space we're testing, we try to get the people away from the floor, and this works quite well. Simple step, a platform of some sort, gets your feet away from the floor, and then typically your sensors higher up from the floor are fine. So we tend to try and really maximize the effort we put into our calibration zone, and then we try to get the person, we create experiments where the athlete or the patient can return to the calibration zone between test recordings. That's very important as well. And we tend to also recalibrate our system whenever we notice something's looking a bit off, or that's just one way where you can reset everything in your calibration zone. Also, something that can happen and something to be aware of is that your sensors can become magnetized. That's, for example, if you leave one of them in a space where there's a very strong magnetic field. A typical example would be if you put one of your IMUs down on a speaker or something with a large magnet. There are ways to fix those, but typically that will create a lot of error in the data coming from that sensor. And then also, if you're trying to improve the tracking during dynamic motions, it's important to be aware of vibrations and impacts that can really cause like temporary errors in the data. And one of the ways you can do this is just by placing the sensors on parts of the body that are able to track rigidly with the bone, and also that are away from, so if you can put them on a part of the body that's not as distal, that can also help in some cases when they're very fast motions and high accelerations. But the best you can do for these type of problems is really taping the sensor down, making sure that it's really rigidly connected as possible to the body. And in some extreme cases, you might even consider using small material inserts for cushioning. And then it's just important to know that some IMU companies allow you to recalibrate your sensors and so on. And they have procedures that you can do in your lab for that. So on top of the motion tracking type of problems that you might encounter, I think the most important thing that we need to understand when we're assessing quality of our data is the effects of our calibration, which is the relationship between the technical frame and the anatomical frame, and also just how our model is calculating things. So I don't want to go into the complexities of the modeling, but it is important to check with your IMU supplier about how they're defining the body model, the anatomical frame, directions of the axes, the type of joints that they're using, and so forth. There are obviously ISB recommendations for these, but it's important to check that when you're comparing data across systems or whatever, that you're comparing apples with apples. And so there are important details regarding the rotation sequences that are used to extract Euler angles, and especially important to understand what post-processing is being done on the data after it's being measured. For example, when the joints are being constrained in some way or data is being smoothed, that's also important just to understand that that's happening. And then when it comes to the calibration, there are several ways that we can now estimate the relationship between the technical frame and the anatomical frame. One that's not really recommended is just trying to stick the IMU onto the body in such a way that you sort of with your eye try and line up the axes of the sensor with the body axes. I think that will lead to a lot of errors. This has been done in some cases, but I really don't think it's recommended. There are some functional movements you can do, functional calibration. This is where you try and detect where the bones are by using some sort of assumed movement. And this can work, but it's only really valid for certain parts of the body. So what most IMU systems are doing is providing a static pose type calibration, and this is what we're seeing on the right here. Different poses which put you in assumed positions, usually sort of neutral or 90 degrees of flexion type of positions. And these are assumed positions that we're not measuring how you're sitting, but more controlling it. And then there's a final way to try and detect where the body is, and that's using anatomical landmarks. So that would be actually measuring where the body is using some sort of measurement tool, and then using that information to feed into the IMU system so that it actually gets a registration of exactly how you were standing during the calibration. So those are the two factors, and then just want to talk about the ways we can check our data. So of course, once you've done some recordings, it's important to do regular checks on your data. So you can start just with visual checks. We check, for example, during our experiments that the sensors have been placed correctly on the body. You won't believe how many times you can swap left and right and so on. So we before every recording and after every calibration we check using a standard movement that all the segments are connected correctly, and then you can do some visual checks to see that your data's fidelity is good. You can have known positions, put the feet together, put them in front of each other, have some sort of check like that. The next kind of level you can have is where you do video comparisons. So here we've got an example on the right of a way to try and see whether the measured signal that we're getting from our model on the left matches roughly with what we can get from our drawing tools on the right. This is again not exactly ideal because you might actually be incorrect in your video tool, but if you're doing sanity checks, sometimes it's important just to see whether they're telling the same story. And of course you can check your measurements of certain joints and see whether they're even physiologically plausible. So if you're getting high ranges of motion on joints that are relatively stiff or close to a hinge, for example, the typical one everyone uses is the knee. The knee is essentially a soft hinge in many applications, and so if you're getting 30 degrees range of motion on your knee rotation, probably this is not really happening on a healthy patient or a healthy athlete, for example. So you can apply some discretionary checks on the physiological plausibility of your data. But if you want to go into the direction of validating your IMU system, again, one can use sort of mechanical linkages or some sort of controlled robotic arm or whatever, where you know exactly using an encoder or something what exact angles you're getting between two segments. But most people, again, are going to be doing something with another motion capture system, probably, again, something like a camera system and some other model using markers. So here's just a quick snapshot of some results we got from comparing our IMU model outcomes during walking to our Vicon system and the standard plug-in gait model. What I want you to see here is just that this is now the errors or the difference in the angle on average across a group of people during walking. And we're looking across different joints and planes, and you'll notice that many of them are over the green dotted line, which we set at 5 degrees for a minimum kind of meaningful difference, smallest meaningful difference. And with a direct comparison, you can see that it seems like the IMU system is actually underperforming a little bit if you just look at it on the surface. But it's important to remember that these differences are all a combined result, or it's a combination of a lot of differences between the systems. For example, the IMU system, in this case, we used a static pose calibration, whereas the optical system used the landmark calibration and had different technical frames because the markers were stuck on the skin and the sensors were stuck elsewhere on the body, which means there are different soft tissue artifacts. And of course, there are differences in the measurement areas between the systems as well. And so we really were interested in understanding the role of the different parts of the system differences and where the errors were coming from. And so what we did is, you'll see in the blue now, this is the calibration normalized data. So we actually took the data from the Vicon system and applied a landmark calibration to the IMU data. And what we saw was a dramatic reduction in some of these angles. For example, the pelvic tilt and hip flexion differences were reduced significantly, and it's simply because of a quite obvious thing in hindsight, that the pelvis during a static pose calibration is assumed to have no tilt. And of course we know that most people, when they stand in a sort of neutral standing position, have at least something between 5 and 15 degrees of pelvic tilt. And so actually what we were seeing here was largely a result of the differences in our assumptions for our model and in our calibration. I just want to quickly, I'll come back to the calibration part because that's something I want to highlight. But basically, the next thing that you'll often see is that a lot of IMU systems are now starting to provide data for model translation. So traditionally, the application of IMUs was to use them as 3 degree of freedom systems, so no translation. So as you can see in the picture below, we've got a skeleton, someone's walking, and the traces that you see there are simply just the motion relative to the upper body of the ankle and the knee. And really where we're heading is the future of IMU applications is actually 6 degree of freedom. And so this is the kind of data you get from your from your optical system already, because optical systems track translation naturally. But 6 degree of freedom data is very difficult for IMU systems to do, and this is something that is still under development in many of the products that you'll see on the market. They're able to give you data that visually looks quite good, but the accuracy in most systems is still not the same order of magnitude as the optical systems. But in case you are sitting with a system that you'd like to check, I think one of the simple checks that you can do, if you look in the picture on the right there, is what I would call a zero displacement test. So simply having somebody move around on the floor or the space that you're in and come back to the exact same position that they started at. And what you want to see is this kind of thing where they actually come back to a close enough position on the floor, because the system that's not doing the translation very well will end up putting the model in a different place at the end than where it started. You can also do some visual checks. You can see that the model is kind of getting a certain length, or if you're walking in a certain direction for a certain length that you know, you can do some visual checks to see whether you're getting reasonable results. But if again you want to do something more advanced, validation is important, then you need to use another system such as maybe a pressure measurement walkway. These are very good for getting very exact measurements of where the feet strike the ground and the distances and so forth. And again, you could be using a camera system in your lab, and it might be worthwhile checking if you can get similar step lengths out of your system than the IMU system and so on. Now, thinking again about how translation works with IMUs, it's important to know that we don't really directly measure translation with IMUs. We have to calculate it. And so, IMU systems are not measuring exactly using sort of the same sort of data that a camera system is using. We're double integrating acceleration, or we're using forward kinematics to basically move the model along the floor. And so the key factors that affect for IMUs the translation outcomes would be contact detection, because to make the model move forward we need to know which part of the body is stuck on the floor. And we also need to know how long the bones are that are moving, so that we can use the kinematic chain to detect the movement forward and backwards and so on. So the model scaling becomes very important, that we know exactly how long each bone is, or close enough. And then also just the normal calibration, because if the angles are wrong in the skeleton, then obviously the translation will also go in the wrong direction. So this is just an example of what you could do. We have a treadmill that measures force, and we are able to then synchronize the data between our IMU system and the treadmill, and we did a little study to try and understand how well we detect the contact using the IMU system, because we could check the timing of the forces. We also did an overground study with force plates in our other lab, and basically we found that for walking at a slow sort of natural pace actually provide us with really good results. We're looking at errors within the range of a few percent, 2% on stance phase and cadence, and really in the low millisecond range for the individual contact, initial contact and initial foot-off events. So again, that doesn't mean that the contact detection would work brilliantly for cutting motions or for jumps. So it's really important that when you assess your IMU's applicability to a study or to a service that you want to do, that you understand if its contact detection works for that activity. And then it's really important that we calibrate as close as possible. So sorry, I'm just coming back now to the calibration. I want to finish off with focusing on the calibration part, because as you can see, it's very important for the translation. It's very important for the general angular outcomes that you get from your IMU system. And so I just want to focus on that as we come to a close. So it's really important to understand that the calibration is also interacting with your soft tissue artifacts. And that's why we always calibrate as close as possible to the midway posture. So for example, if you're doing a walking study, you shouldn't calibrate your model in sitting. Vice versa, if you're doing an ergonomic study, calibrating in standing is going to introduce a lot of soft tissue artifacts, because what you'll find is that the sensors just cannot possibly not slide. Even if they're stuck to the skin actually can slide. For example, your pelvic sensor, when you do a sit to stand motion, will really, the skin slides over the bone. So you've got to try and find a compromise where you calibrate, especially for large range of motion activities, in the sort of midpoint between the two extremes. What we do for our static pose is we try to control the feet first, because that's the most, especially in standing, but even in sitting, and then the trunk. So we try to really keep the feet sort of, because from there we can control the pelvis, and we can make sure that the ankles are under the hips. And we usually start in the frontal plane and make sure that that the person is standing as close as possible, although it's not always possible to get them exactly in the position, in the neutral position for the calibration. But we make sure that the feet are parallel, that they equidistant from, that the one is not in front of the other. And then we control also in the sagittal plane, we really try and focus on making sure that the person isn't hyperextending their knees, because when you tell people to straighten their leg, they tend to hyperextend and so on. And it's just important to develop a very strong protocol for how you check, because people also tend to move again after you've positioned them and so on. So we tend to capture actually the position, whether it's by taking photos or videos of the calibration procedure for reference, especially in studies where we need to go back and have a look. And so I just want to quickly talk about how we try to understand these kind of things for us. So this is a person standing in a static pose calibration. And what we did was we put markers on them, and we captured that exact posture with the Vicon system as well. And we measured them independently several times. And we used a trained person who we'd been doing gait analysis with before, and they were basically trying to see how repeatably they could do the same position if they did the static pose many times. And they were also trying to see whether the way that they positioned them was actually as close as what we thought to the assumed posture, which is neutral. And so this was basically a validation of that static pose procedure. And this is a really interesting piece of data. So this, for me, is demonstrating, this is the intra-subject variability during the static pose calibration. So what we're seeing here is the difference between the assumed value of 0 degrees neutral that we assumed for the IMU system and the values for the Vicon system that were measured. And what you can see here is basically the story is that we are able to repeatedly position a person in the same pose multiple times. So if our physiotherapist was able to do a recording, move the person back and put them in exactly the same position, give or take 2 degrees. So we were within 2 degrees in most cases in all the joints. And that just shows that the static pose is really repeatable if you have a trained person implementing it. And that already is valuable information for us to know that the errors that we get when we compare to Vicon, or when we want to understand the validity of our system, that it's not coming from our calibration in terms of the variability that we see. But we did see, very interestingly, that the average postural angles that we measured were very far from zero for some of them. Of course, the pelvic tilt, as I mentioned before, you can see that people are standing in pelvic tilt when they are standing in a static pose. our IMU system assumes zero tilt. And that translates into some hip flexion, of course, if the thigh is roughly perpendicular with the ground. But we found that it was actually less so, and that's because we saw that the person was actually always unable to stand in zero ankle dorsiflexion. And that's simply because if you see the picture here, it's impossible for the hips to be above the ankle simply because your center of mass has to be above the midpoint of your base of support. And so people are typically standing in slight dorsiflexion and slightly less hip flexion than they have pelvic tilt. But this is why we were able to use this information to see that it correlates quite well with the differences that we saw with our Vicon system. And so, again, the slide that I showed earlier just highlighting that calibration was leading to most of the differences. So what this tells us is that when you use a static pose calibration, it's very, very risky to compare your data to the data that you have captured in another system, or to literature where they captured motion capture data with a different model calibration. And that might seem obvious, but in many cases it's important to keep in mind that these differences don't necessarily mean that the data is not useful or valid in certain applications. It just means that the definitions for the 0 points of your graphs are quite different, and so you can't directly compare them. So in closing, an important question then, I suppose, for you as an IMU user is the calibration that you're going to use. If it's a static pose, is this sufficient? What we found is that it does provide a repeatable reference posture. So for in many cases when you're doing services or comparing just longitudinally the results you get for a specific person, patient or athlete, it's actually quite fine in our opinion, because we know that we can repeatably get the person to that reference posture again, even if they come in another time. But it doesn't provide an accurate calibration, which means that it introduces errors into our angular outcomes and translation outcomes, especially when we're comparing to reference data. And so a biomechanical model from an IMU system that is calibrated with a static pose is essentially not fully compliant with ISB recommendations. So the International Society for Biomechanics has recommendations for how body models should be defined in terms of their axes and anatomical frames, and a static pose can't give you that information for a specific person. It's not a personalized calibration. And so I think this brings me to the point where I turn over to Coleman.
Thanks, John. That was a perfect segue. I think primarily who we're speaking to is biomechanical researchers, and being ISB compliant with their models is probably something of interest. And knowing these concerns, we developed this calibration adjustment tool, which helps solve this these model offset set you're discussing. What you can see here is the calibration adjustment tool on the left, which consists of a magnetic source, 2 reference IMUs to align the coordinate system, and a pointer. And the pointer is actually what you use to digitize land and adjust the segment lengths and orientation of each segment. So with John, we were able to work on and develop this and are excited to offer this tool, as an add-on to our IMU system that's fully integrated into our software. And rather than discussing this with you in great detail, I'm just going to let John kind of show some examples of what this can do to your data and how dramatic the impact of a personalized calibration can be. So John, if you want to take them through.
Sure. So just to highlight again, so what I'm going to show you now is a video of just some simple movements that were done with the calibration, first with the normal static pose calibration and then with the landmark calibration using this tool, Just to illustrate, for example, a situation you might typically see in a clinical setting where you have a patient who can't stand in a neutral position for whatever reason. For example, here we have a position where we're about to calibrate, and the system is asking us to assume the position you see here in the skeleton, but your subject here cannot stand in that position and is standing, for example, with some external hip rotation and some foot rotation outwards on the left. And as you can see, our system is assuming that we're pretty much neutral. And so if I now move, if the subject moves back to the actual good calibration position, what you're going to see is that the IMU system is going to incorrectly assume a bad posture. So here we're standing in a much more close to calibration position, and as you can see, because we calibrated in a bad position, we now are totally wrong. And these kind of offsets, so you'll see I do a little squat now, and if you just have a look at the data here, you see the knee flexion for left and right is very asymmetric. In fact, there's very little ankle dorsiflexion. If you look at the green line here, when I do the movement, it's not registering at all that I'm flexing my left ankle. And what I'll now illustrate to you, this is just showing you, if you have a look at the avatar, it's just to illustrate that the motion is now corrupted by this poor calibration. So the skeleton really doesn't look good. What we're going to do now is apply the landmark calibration. So I'm going to click on a button on the right just to say calibrate by landmarks. And what that's going to do is use the data from the pointer to register exactly how the subject was standing. As you can see on the skeleton on the right, and on the left, the points that were collected for those are the landmarks. And so we're able to register actually the correct position, which essentially is a very exciting feature, because what it means is that we can, no matter how you stand, it doesn't matter, the system can calibrate you. It's impossible to calibrate a patient, for example, that cannot stand in one of the assumed postures for a static pose. And here we're just providing an absolute breakthrough for people that can't use an IMU system on certain populations. And it's not just about getting better data. In some cases, it's making certain things possible that weren't possible before. Now I'm playing the same recording back with the better calibration. And some of you might have already noticed that in the section now where I'm going to do the squat, you'll notice that the flexion for the left and right are now very symmetrical. And you can see it's because the movement wasn't that pathological. So previously our data seemed to suggest that it was very asymmetric, and now with the proper calibration you can see the symmetry is right there. There's the dorsiflexion from the ankle on the left. It's simply because we've started the model in the right position. And so we're getting just a much better result because of the landmarks that we could measure with the calibration tool. I'll illustrate another example to you in a sitting type of scenario. So again, you might have some patients who struggle, maybe they're a stroke patient and they have or some other disability where they cannot sit in the right posture. And in this case, I'm going to show you again just the way in which the assumed posture, if you'll notice, is so different. We have to assume for a normal static pose a 90-degree angle or some assumed angle. And you can see I'm sitting in much less knee flexion than 90 here. And there's some hip adduction as well. So the angles here are close to 0, and the knee flexion with the original calibration is assuming 90, but you can see that that's not the case. And if we apply this calibration by landmarks again, what you'll see is that it will display again the sitting position that we're in, and now we have the correct posture for the model. And you can see, for example, the left and right knee flexion is now much less, 70, which looks at least feasible. And you can see that the feet are outwardly rotated, and that's what we have for the external foot rotation. We're now not assuming 0 anymore. And the last video I just want to show you is this, the application of this. So if we had done an assessment with an IMU system without the landmark calibration tool, and this is now obviously a gross example of a poor calibration, but you can imagine that even 5 degrees of difference in your calibration could actually filter through. So here I'm going to play you the adjustment that is made now in a sitting position back to what is assumed to be the calibration position. So that in most people's mind would be considered a decent calibration for sitting. And yet, when you look at the calibration tool, what you're seeing is that it's still not what we would have assumed. So although I look at the video and think, okay, I can calibrate that using the original calibration, you can see the knees are actually not flexed to 90, the feet are not exactly parallel, and so forth. So even good calibrations that we might think are a pass, the landmark tool often picks up that we were wrong in the same way that we saw with the Vicon data. So this is essentially giving you the ability to have a Vicon or optical motion capture level input for your calibration for landmarks. But it's portable and it's something that can be taken with you anywhere, so it doesn't really break the whole advantage of the IMU system, which is the portability. So whether it's just to improve data that you think is already relatively reasonable, as we said, making it ISB compliant, is one advantage, and obviously the other would be that you can actually test different populations and it opens up new possibilities. But yes, I think for me, the most exciting part is that finally with this type of tool, we're able to get the data that much closer to the kinds of information you can get from a camera system without compromising the mobility or the portability of the system. And that's really, for me, why this is such an exciting product.